Good afternoon, and thank you for joining us for today's webinar on leveraging your annual boiler shutdown. My name is Amy Rotler, and I'll be your moderator for today's presentation. For those of you who are not familiar with our WebEx setup, you have been muted upon entry. So if you are having difficulty with the audio or video, please submit your questions to all panelists using the Q&A tool on the control panel of your screen. By selecting all panelists, we can make sure the appropriate person sees your question or issue and can get you squared away as soon as possible. For those joining us for the first time, Cleaver-Brooks offers monthly educational webinars on various topics. I encourage you to visit our website at www.cleaverbrooks.com/webinars to see a list of our archived events as well as what's coming up in the near future. Next month's webinar is titled Are Boiler Stacks Exhausting? Following the completion of this webinar, you can go to the webinar section of our website and register for this webinar as well as view a more detailed description of the topics to be covered. Today's presentation will last approximately 40 to 45 minutes, and we'll leave about 10 to 15 minutes at the end for any questions you might have. Also, Cleaver-Brooks is now providing certificates of attendance for those who would like a record of your participation. Our webinar should equate to 1 professional development hour, and you may download a copy of the webinar's description and/or PDF of today's PowerPoint should you need to submit to your local agency for PDH acceptance. Most of you indicated your desire for a certificate upon registration. However, for those who did not and wish to receive one, you can just add a note to the survey you will be automatically prompted to receive at the end of this WebEx presentation, or you can send an email to marketing@cleaverbrooks.com. With that, I would like to introduce our presenter today, Steve Connor. Steve has been in the industry for well over 40 years and has been very instrumental in the development and advancement of our training department. Go ahead, Steve.
Well, thank you very much, Amy. Today we are going to be addressing a very important issue, and the opportunity of which is often overlooked, I believe, by many because of the disruption it causes, along with the considerable work connected with the process. Leveraging your annual boiler shutdown should be part of your boiler room standard operating procedure because of the many benefits that can be attained if the shutdown is approached in the proper way and appropriate action is followed and taken as a result. The benefits of taking advantage of the annual shutdown impact specific areas such as safety, reliability, sustainability, and energy conservation. And with ever-increasing emphasis on the bottom line today, saving energy dollars is a big plus in controlling operating expenses, especially in view of the extreme competition we all face within our widespread global markets. So with these factors in mind, we are going to first take a look at a boiler room and see what it holds in terms of possible problems. And then we'll properly shut the boiler down and isolate it. From here, we'll open the boiler up and see what to look for on both the water side and the fire side, including what should or should not be done based on what we find. And then we'll look at the piping and controls on the boiler with emphasis on the condition, and if any, and what upgrades may make good, sound, economic sense, especially as it relates to safety, reliability, and the significant costs associated with operating the boiler. Remember, that boiler consumes over 4 times its initial cost every year that you fire it. So, starting with the general overview of the boiler room, we're looking now at the boiler still in a live condition. Nothing's been shut down. So we take a clipboard and we start walking around the boiler room and looking for various things while it's still under pressure. We're looking at piping, valving, as you can see here. We're looking at the feed system, looking at the pumps. Is there any bearing noise? Is there any cavitation noise? What about the pump seals? What about the packings? Now, in some cases, they're expected to leak, but not profusely. What about the alignment of the pump and the motor assembly? What about our water softener? What about the brine tank? Is it filled with salt? Is the brine level up too high in the tank? Is it at the proper brining level? These are the kinds of things that we want to look at, because it's not only, when we look at a boiler and what it consumes in energy, The boiler is part of a system. They all work synergistically together, all in a coordinated fashion. So any one of these elements can cost us significant dollars. And it's not just the fuel dollars, it's the safety within that boiler room complex. You know, back a number of years ago, back in 2002, Hartford boiler inspectors completed a 10-year analysis of what was causing boiler incidents, what we call in this business occurrences, but some people refer to as explosions. And what they found over this 10-year period of time is that the precipitative causes were mainly poor maintenance, which was a result of improper training of boiler operators, and also the low water cutoff, which caused the problem with the boiler to disengage from its foundation, if you will. So in some of these cases, it was not just extreme damage to the property, but also death or serious injury to body. So the survey is complete. We've walked through that boiler room, and now it's time to pay attention to the boiler itself. And what we're going to be talking about today, even though for time reasons we're going to be using as examples primarily the fire tube boiler, it really, the things we're looking at apply to a water tube as well. So once that boiler is shut down and it's opened up, and we'll talk about that too as we go through here, we're going to be looking at the various components and assemblies that are related to that boiler and see what there is that we can do here to improve the efficiency, reliability, and the safety of the unit and of the facility itself in which this boiler is contained, in the boiler room. Now, before we go into that, though, let's talk about shutdown. How do we properly shut these boilers down? Well, first of all, we put the boiler in the manual mode or in low fire. And then we blow down the boiler, not just the boiler itself with the quick and slow opening valves, but we also blow down the water columns, the primary and auxiliary, and the gauge glass. We shut off the burner at that point, and we allow it to go through a post-purge. We then isolate and tag the fuel supplies. We close off and tag the boiler's main stop valves. That would be the stop and check valve coming off the boiler in the piping above. We isolate and tag the electrical power. We open all drains in the steam line. Here what we're trying to do is break any vacuum that might be forming and begin to drain that piping around the boiler itself, coming off the header. We open the boiler vents when we get down to about 10 pounds. We isolate and tag the feedwater supply. We allow now the boiler to cool and for that pressure to get down to zero. We then open the bottom blowdown valves and we drain that boiler out. And then we open and access the doors in both the front and the rear. Now some boilers may have two large doors. A 4-pass dry back boiler will have two large doors. A wet back boiler will have an opening in the front for the burner and of course an access way in the back. Then we close the flue gas outlet damper if you have one. So now the boiler is cooled, it's drained, and it's ready for us to take a look at it, and let's optimize this shutdown. Let's leverage the shutdown now for benefit. As we walked around the boiler, we noticed that we had a handhold plate on the side of it that was leaking and actually spewing steam. Now it really wasn't steam, it was condensate at that point, but obviously the gasket was compromised here. And what we're looking for when we take this handhold plate out, we're going to find probably that the surfaces of the plate as well as the boiler seat itself have been etched by this steam. So it's going to have to be sanded. Both those surfaces are going to have to be sanded and smoothed so that we will get a good, proper seat with that gasket. Now we could either use a neoprene gasket in this particular case, which has got a rating of about 180 pounds or 380 degrees Fahrenheit, or depending upon the extensiveness of the etching, we may have to go to a more sophisticated or a better steel, if you will, the gore joint sealant that we've often recommended, which will fill in some of those void areas that we could not sand out. That's got a capacity of 3,000 pounds or 600 degrees Fahrenheit. Now, when we looked inside the handhold, this is also an opportunity to take a look at the water side of these fire tubes. Is there any scale on them that you can see? Is there any bridging of these tubes by scale, which would be a huge evidence that the water treatment program is kind of gone to hell in a handbasket, if you will. So if we see evidence of scaling, which let's say it's 1/16 to an 1/8 of an inch, that boiler may have to be acid cleaned. Or if it's extensive, we'll be taking a look at those tube ends in just a minute. The tubes may have to be replaced. In either case, acid cleaning or replacement is about the same cost. We now go on top of the boiler. If this will move. Can't get my, won't advance. We now go on top of the boiler and you're going to find a manway. Now, in this particular case, the manway looks in good shape. But when we take it out, it's very, very important that we look at the condition of the gasket. Is the gasket dried out? Is it brittle? Is it cracked? And if so, we may have to replace it again with possibly a neoprene gasket, as you see here in the upper picture, or maybe a spiritalic, or possibly a foil-reinforced graphite gasket, as you see here. That graphite gasket, by the way, has got a tolerance of 2,000 pounds and a 1,200 degree Fahrenheit maximum temperature. So now that we've got that handhold plate out, or manway I should say out, we now have a good chance to take a look at these tubes up on the top of the fire tube boiler. And as you can see that there's really no evidence of scale here, but I do have significant evidence of corrosion. So this tells me right now that I've got a problem with my deaerator or my sulfite treatment. I've got some serious problems with this boiler relative to oxygen corrosion. When I open up the door, I find what has happened because of that pitting. It's not just blisters on the top of the tubes, but we've actually drilled through that tube itself, right through that 105 tube wall, allowing water and steam to spew into the fire side of the boiler itself. So you see the accumulation of calcium, you see the evidence of what's happened here in terms of the leaking. So this boiler has really been compromised as a result of this, and possibly if this has a refractory filled rear door, that door was damaged as a result of the steam and water accumulation in the rear end of that boiler. So now the inspector comes, as you can see here on the right, and obviously he sees the problem. The tubes are extended, they're cracked, they have to be replaced. What we'd like to see is something as pristine as you see here on the left. Of course, it's not going to be that pristine when it's under that much heat and pressure. But you want to have a good, solid seat between the tube sheet and that tube. No compromise, and I'll show you that in just a minute. This particular boiler has gone through some real havoc, and those lower tubes have to be replaced. So it requires a couple of men to come in and cut those tubes out and replace them. Now, most of the time in these fire tube boilers, you're going to find the hot area, or the second pass, what we call the hot pass, is the most vulnerable to scale overheating, cracking, and having to be replaced. Now, this particular unit has been, the tubes have now been replaced, but they have not been rolled, or I should say they're rolled and expanded, but they have not been beaded, or they have not been welded as yet, as you can see here. That's a very, very important procedure. Because you see, if I bead a tube, I want to make sure that that end comes in contact with the tube sheet. Remember, I've got water on this side. I've got very high temperature on this side. I've got a great delta T. So I can transfer the heat, but this edge has to come in contact with it. So I've got my heat sink to be able to deliver the heat from the tube into the water. That's a beaded tube. You got to make sure that that end of the tube is beaded to the tube sheet. In a welded tube, you've got to make sure that that weld is coming in contact not just with the tube end, but the tube sheet itself. Extremely important. Now, the other thing I want to look at when we're going around this boiler is what about the Feedwater connection on this fire tube boiler? If you see any evidence here of any cracking, that coupling has to be replaced. So you could replace it with a coupling, but some manufacturers offer what we call a thermal sleeve. It does two things. It not only repairs the problem that we have, but also provides a thermal sleeve wherein some of the water from the boiler itself, that hot water, comes between the coupling and the sleeve itself, the outer pipe, and preheats the feed water as it comes in, which will minimize this particular problem from occurring. What's happening here is thermal shock. That's what's causing it. Remember, you've got a boiler, let's say it's operating at 100 pounds, that's 338 degrees on the water side of this boiler. Let's say you've got 180 degree feed water coming in here. That's quite a difference. So if you've got a lot of modulation going on as far as your modulating feed water valve, or it's an on-off pump operation, this particular connection can go through a lot of stress. A thermal sleeve can help thwart that problem. We're moving now from the pressure vessel. Let's start looking at the refractory. Here you see a fire tube boiler, not in very good shape right now, but I want to call your attention to the rear door. Now this refractory that you see right here is high temperature castable material. It's being exposed to temperatures nearing 2,000 degrees. If I look closely at this door, I don't really see any cracks that are 1/8 of an inch or greater. Even though the boiler is not in very good shape, this door, for some reason or another, is okay. It just has small cracks. Small cracks less than 1/8 of an inch will seal themselves when the boiler is under fire. So nothing has to be done to that door. Now here's another situation, though, where I see some cracks in that door which are over 1/8 of an inch. Now, this has got to be fixed. If I don't, it's going to further deteriorate the refractory, and it's ultimately going to get to the steel of the door and warp it, which means the entire door would have to be replaced. So here, what I can do is I could pound plastic. I could etch this out a bit and pound some plastic in it, or I can fill it with a refractory patch and then wash coat it. The main thing, though, to remember here is that this door is repairable. Make sure you make the repair properly to extend the life of the door. These doors will last a long time if they're properly cared for. Now here's a situation where we've got, something that the door is essentially shot. What you see here is not just extensive cracking in the lower portion of the door, but also the baffle has been compromised. What's happening here now is this baffle will separate my second and third passes, okay? Or the first and second passes, I should say, of the boiler, the first and second. So if I have any damage to this baffle, that means that gas, that hot gas coming out of the second pass is going to bypass into the third pass and come through the boiler. It's going to increase the mass flow. It's certainly going to increase the temperature. My overall efficiency goes to heck in a handbasket. My temperature in the stack, of course, is going to rise. Needless fuel dollars being poured out. This door has got to be replaced or repaired, which means the entire thing has to be repoured, including the baffle. Now note also this little sleeve right here. This is a refractory sleeve that is insulating the sight port of the boiler. In other words, from the rear of the boiler, I'm now looking down toward the front end and actually looking at the burner flame. You'll notice this cooling line. This emanates from a plenum in the front, from the burner plenum, and provides air to the sight port to cool it. If this is compromised, if this is disconnected or crimped, and I don't get sufficient cooling, that refractory sleeve is going to crack, and we're going to start causing problems with our door. It's going to overheat in this area. Well, we'll move now from the rear of the boiler to the front. Now, this is a 4-pass dry-back fire tube boiler. What we're looking at is the front door, which in this particular case, because we're looking at lower temperatures here, we're using a fiber blanket for an insulating material. Now, this could be a castable as well, which I'll show you in a second. And it's being held in place with a screen mesh, a stainless steel screen mesh, and pins and clips. So what we're looking for, if you have a door such as this, you're looking for any erosion of the fiber blanket material. You're looking for compromise of the net, the screening chicken wire, if you will, that's holding that fiber insulation in place, and also missing clips and pins. There's a rigidizer that's also put over this refractory, or this fiber blanket, because the gases coming out of these tubes as they reverse and go down another pass are traveling at about 50 to 60 feet per second. And that's a fluid. Those gases are like a fluid, and it's abrasive. So we put a rigidizer across this to minimize any compromise of that fiber blanket. Now here you see an inner door in the front of the boiler that had a refractory seal, not the fiber blanket. And obviously it cracked and then a large chunk fell out, which has to be replaced. The good news is that there are repair kits available today to fix problems such as this. And it's an easy fix. They come complete with all the materials that one would need, including all the instructions that you need to execute the fix on that particular door. We'll move now inside the boiler, and we're looking at the refractory inside, which we call a throat tile, and a furnace liner. But right now, you can see that the service technician is checking out the throat on this boiler. This is a water tube boiler, and here he's checking out the throat and liner on a fire tube boiler. This particular boiler is about 1,500 horsepower. Now, what he's looking for is any compromise on this throat tile. Any large cracks or any cracking? Are there any chunks missing? What about this furnace liner? Looking for the same thing. These are very, very important, because when we're looking now from the front end, this flame is now coming toward you. This throat tile does two things. Number one, it insulates, but it also shapes and aids combustion, because as this heats up, it gets very hot. It glows, and it does assist combustion. It also helps shaping. The furnace liner that you see here will protect the furnace from the extreme temperatures in the very, very front of that burner. Very, very important that this not be compromised, it not be cracked, and large chunks not missing. If you see that, it's got to be repaired. In some cases, we've seen the entire throat has to be replaced. Some cases, the entire liner. These are there for a purpose. They should not be compromised. Now we're looking in a water tube boiler. This is a commercial-sized water tube boiler, about 100 horsepower. You can see here where the throat has been compromised. That's got to be repaired or possibly totally replaced. Now here we're looking from the front of the boiler, took the burner off, and looking down toward what we call the target end. This is the access way into this commercial-sized water tube boiler. Everything looks in fine shape. The furnace floor, which is protecting these riser tubes, in fine shape, as well as the refractory in the access door itself, and the sight port. Moving now away from the pressure vessel and the refractories, let's start looking at some of the assemblies. The burner assembly, for instance. Now what you have here is what we call a burner drawer assembly. We have the burner drawer right here, and we have the housing, the burner housing here. Now you see them separated, the burner drawer, the burner housing. This not only holds or encompasses the burner drawer, it also provides the gas entry, okay? I've got a gas burner now, and the manifold of that gas line or gas train connects to this connection right here and fills this burner housing with pressurized gas, with natural gas. And what happens is the gas then comes out of these orifices, which in this orifice type housing is 360 degrees. I've got orifices all the way around. So that's the relationship between the burner drawer and the housing. Now this is a little different type of port. It's called an annulus port, so the gas comes out of this annulus that you see here as opposed to orifices over here. But the burner housing serves the same function. So what I'm looking for here, I'm looking on this housing if there's any evidence of any cracking or warping, where obviously I've had some excessive heat. And that would be an example that you will see here. This is a burner housing that has been compromised by overheating, and it's cracked. Now, it's possible that we could fix this. We could weld it. But if not, it may have to be totally replaced, and they can be. But in some cases, they can be repaired through welding. But that's what you're looking for, because if I don't do anything about this, I've now got uncontrolled gas going into the combustion area, which is going to manifest itself with a very unclean burn and a lot of rumbling. It's certainly something that you don't want to mess with this. So if you see any evidence of that, make sure that you take corrective action, either repair or replace that housing. Now, as far as the burner drawer is concerned, what I'm looking for here, this is what we call a diffuser, and every burner is going to have what they call a burner baffle or a diffuser. What happens is the air is coming through the damper and coming through this diffuser. These fins allow it to take a pressure drop and highly spin this air so that I pick up the gas just in front of it through those orifices. This diffuser is just behind those orifices that I showed you previously. So if you see any cracking, warping, bending, or any deformation of this diffuser, it's got to be replaced. This cannot be repaired. It's got to be replaced. This is extremely important to be able to achieve a high combustion efficiency. Here's the other area we want to look at. This is a rotary damper. I've got a sleeve within a sleeve. Sometimes this warps or the bearing wears. This sleeve, this little inner damper, if you will, has got to move freely. One little finger on the lever must allow you to be able to move this damper open and closed. If not, that bearing's got to be checked. That particular rotary damper may have to be replaced if it cannot be fixed. Very important that that happen. The next thing we want to look at, as far as the burner is concerned, we want to look at the scanner, either UV or lead sulfide scanner, to make sure there's no evidence of any cracking of it or any clouding of it. It's got to be, in very good shape for it to be able to pick up that flame signal. We're also looking at the pilot tube here. It has an electrode. The electrode is what is providing the heat or the spark to ignite the pilot. If this electrode is corroded or burned, it probably will not have the proper gap to give me a good spark to ignite that pilot. If you've been having pilot problems, this could be the cause. Also, sometimes this electrode will burn through the pilot tube and cause problems. So look at those two things. So now we are at a point where we can close the boiler up, and to do that, we certainly have to have the proper gasketing and follow the procedures that the manufacturer calls for when closing these doors. Sometimes they will recommend that you begin to adjust the bolting at possibly starting at the 2 or 3 o'clock and then whatever the rotation might be, but seal it the way they are telling you to seal it, and then torque it accordingly. And then, of course, before you do that, you put in the proper gasket. This could be a tadpole gasket. You'll also be using probably some rope gasket to seal the baffle against the tube sheet. We've got other types of gaskets. These are segmented gaskets that could be used, or it could be a whole gasket. This is probably one that would be used for the burner drawer. And then, of course, we've got these neoprene gaskets that can be used for the manways or the handholds or the other type of material that I mentioned before. But make sure you use the proper gasket, that it be a good gasket. Now, if you open up the boiler and you find that the gasket that you have is still pliable, still in good shape, well, maybe it's a tadpole, let's say, it's still in good shape, you could probably reuse it. But don't second guess it. If it looks questionable to you, replace the gasket. Believe me, it's money well spent, because it's a cheap fix for a major problem if that door is not properly sealed with the proper gasket, or the handhole, or the manway. So now, leaving the pressure vessel, the refractory, and the gasketing, let's start looking at some of these assemblies. Let's look at some of these controls. Here you see a single point positioning system. And by that I mean I have a damper motor here, or a drive motor, that's driving this linkage assembly. I've got a horizontal shaft coming across here, and I've got the linkage arms that are connected to my air and connected to my fuel. So it's a single point positioning system. The adjustments are made through the linkage arms and then also this cam assembly that you see here. So through the combination of adjusting the linkage arms and the cam, that's how I establish my fuel-air relationship. Now, the problem with this is that these bearings have a tendency to wear. We begin to develop hysteresis or stretch and wearing. And as a result, especially with a burner that modulates a lot, we don't get the repeatability in terms of fuel-air ratio control that we should have. We would recommend, at least our experience dictates, and other manufacturers might say something else, but we would recommend that you seriously look at what we call parallel positioning. Because with parallel positioning, we take that stretch, hysteresis, and wear out of the equation. We've got motorized actuators now that are independently controlling our fuel and our air. This takes the mystery out of it. We now have repeatability, we've got precise control. These then are feeding signals through a central control unit, and we make adjustments accordingly. That's how we set the fuel-air ratios. Of course, when you do this, we're saving energy too. Because if you've got a boiler that modulates a lot and it's got a single point positioning system, you're probably looking at fuel savings in the area of 1/2 to 2%, anywhere from 1/2 to 2%, depending upon the amount of modulation that burner is going through during the course of a day. Now, speaking about savings, we shouldn't forget about the secondary fuel supply. If we've got, let's say, number 2 oil as the standby. I've been in a lot of boiler rooms where the oil is used infrequently, but when it is, it leaks like a sieve. And the corrective action is a bucket underneath the fuel controller or a rag. That shouldn't be. If you see any evidence of any of your control valving leaking in any way, that should be addressed. And many times it's just nothing more than tightening or replacing gaskets and then tightening. So don't forget that alternate fuel. The controls that actually turn our boiler on and allow it to modulate. These are the pressure controls. We've got an operating control, we've got a high limit control with a manual reset, and we have a modulating control. What we want you to look at here, take a look at the wiring. Is there any evidence of any overheating? Is there anything that these wires may look brittle? What about the mercury in these switches? Is it caramelized? Is it browned? If so, replace that control. That should not be. Now, Also, if you have let's say a pigtail siphon, right now we've got vertical cooling stanchions, if you will, coming off this manifold. You don't want any steam to hit these controls, by the way. That's why we've got this pipe right here, which will allow cooling of that steam so it condenses. Now, sometimes you have a pigtail siphon. I've been in boiler rooms where the pigtail siphon is actually, the loop is parallel to the manifold. You don't want that, because when it expands and contracts, it's going to move left and right. Okay, and it's going to have an impact on the switch. So make sure if it's a pigtail siphon, it's perpendicular to the horizontal pipe. Now, there's a lot of companies today that are saying we don't want mercury in our plant. A lot of hospitals today are saying that. So there's fixes for that as well. Honeywell has come out with this control that doesn't have any mercury, and it's a combination control with an operating, high limit, and modulating control all in one. This high limit control is here. This is a UL requirement that we had to put another control on this particular boiler. But all the controls are really in this one single unit, operating, high limit, and a modulating control. No mercury. Here's a Danfoss system with Danfoss controls, no mercury. In this particular case, they're using a pressure transmitter which is being fed back to a PLC, which is really their modulating control. So what we have is the operating control, the high limit control with high limit, and your modulating transmitter right here. The low water cutoff, very, very important control on your boiler. As a matter of fact, the most important control on your boiler. Check the head switches. If you've got mercury, the same as I mentioned for the pressure controls, check, is it still silver? Any evidence of caramelizing? Any evidence of these wires being brittle or overheated? If so, change out the head. Don't do anything with this control, with this switch head. Replace the head. Here's one with snap acting switches, because mercury in this particular case was outlawed. Make sure that there is no compromise of the gauge glass. You're looking for etching, which could be caused by alkalinity. If it's etched in any way or cracked in any way, replace it. As far as the low water cutoff is concerned, that should come off, and look inside the bowl to see if there's any evidence of any scale or sludge building up. Also, the piping. We don't want the piping to look anything like this. This is extremely dangerous. We've seen evidence of low water cutoffs during the annual inspections that look something like this. And I think at this particular point, when you see this, you understand that the people in the boiler room don't understand what's going on thermodynamically with that boiler. That you really have a controlled bomb in that room is what you have. You got to understand the power of steam. Did you know that 1 pound of water at 212 degrees in atmospheric pressure occupies 0.017 cubic feet, but when we go through the latent phase change, it expands to 27 cubic feet. That's a big expansion. Did you know that 100 gallons of water at 100 pounds, if released uncontrolled, generates, yes, 7 million horsepower? Did you know that fighter jets are catapulted off an aircraft carrier by a steam catapult? They weigh 60,000 pounds. They go from 0 to 165 miles an hour in 2 seconds. 500 horsepower fire tube boiler holds 2,300 gallons of water. Compare that to 100 gallons. So just imagine the power. And a 500 horsepower boiler weighs about 60,000 pounds, the same as that jet. 0 to 165 miles an hour in 2 seconds. So now we have a situation where that low water cutoff looked like this. Looked like the one that I had just shown you. And so now I've got a process that's going on. The pressure's not dropping because my process is taking the steam. but I'm not introducing any feed water anymore, and I continue to evaporate until I get down to the furnace here. And now this furnace is cherry red. The pressure all of a sudden begins to increase a bit because a part of my process shut down. It was satisfied. That caused just enough pressure to force that float in the low water cutoff into the sludge. It triggered the feed water pump. I got a huge differential now between the furnace and the water coming into my boiler. Bang goes the furnace. It's what we call a bagged furnace. All the water that's left in that boiler now evaporates and expands 1,600 times. The boiler comes off its mounts. It rips off the 8-inch valve. It traverses across the boiler room, out the wall, and hits this cooling tower. In this case, thank goodness, because across the street was a school and the playground was full of kids. The rear door at the same time blew off the back. This all happened in 2 seconds. Knocked out the wall and took out part of the roof, as you can see here. This is nothing to fool with. Now, some people will say, well, what happened to the safety valve? Why didn't the safety valve save this from happening? Well, let me tell you, as I mentioned, the pressure wasn't building. The safety valve had not reached its limit because the users were taking that steam. It was the fact that the low water cutoff failed. I introduced feed water and the boiler exploded because the furnace bagged. So, but the safety valve is an extremely important control on this boiler because if the operating controls fail, that's when this has to come into action. If your high limit control with manual reset doesn't shut that boiler off in a pressure rising condition, the only salvation you have between here and infinity is the safety valve if you're in that boiler room. So it's very, very important that that be piped properly and that it be checked every year to make sure it's operating properly. And as you can see here, lift the lever at about 75% of the setting or greater and allow enough time for it to blow for a bit, just a couple seconds, to make sure the huddling area is cleared of any type of sediment so it properly reseats. Now, we go to great extremes during these webinars not to become a commercial about some of our products, but I think I would be remiss if I didn't at least mention a control that we came out with to try to mitigate or prevent problems that you just saw with boilers taking off and leaving the boiler room. It's called the Level Master. And I'm not going to go into any details about what this is and make this a commercial, but I would encourage you that if you want to know more about this Level Master and what it can do to keep that boiler safe and those people in that boiler room and in that building, I would encourage you to visit our website or talk to one of our manufacturer's reps, one of our representatives in the area, to tell you about it. That's all I'll say. Now, the other thing we want to look at as far as controls are concerned is the burner management system, also known as the programmer or the flame safeguard system. Now, this burner management system has gone through a number of evolutions, or a great amount of evolution, since I've been in this boiler business over the last 50 years. It's gone from the tube type to the mechanical type to the solid state to the microprocessor type. And these are all, what they've done is we've enhanced the overall communication to a bit, fault codes, allowing technicians and operators to find the fault more quickly, more readily, and keep that boiler online or get it back online as quickly as possible. So that's how it's evolved. As far as the sequence of operation, nothing's changed. Nothing's changed at all. The sequence is still the same, even back in the days when it was the old tube type compared to the microprocessor type today. It still goes through the same sequence. But what has changed, though, is that these microprocessor type controls, the flame safeguard programmer or burner management system, whatever you want to call it, has now been incorporated in many cases to a PLC back platform. Now, What the PLC platform allows us to do is to expand the communication, to give our operator a lot more information about what is going on. We can also trend fuel consumption, steam consumption, feed water consumption. We can trend all sorts of information so that we have a better grasp about what is going on with that piece of equipment that consumes 4 times its initial cost every year in fuel. The more we know about what we have going on, the better off we are in controlling the whole situation. We have an HMI here, a touch screen. So now, rather than this operator climbing up on a ladder 15, 20 feet to get to a pressure control to adjust the settings, he does it right here, or she does it right here at the HMI. Lots of innovation has gone into this. The other thing that we can do is we can expand this system to include things like variable speed drive or oxygen trim, all those things that will help us improve the overall efficiency of that unit and what it consumes in terms of energy, both fuel and electrical energy. So once we've got that boiler checked out, we've made decisions on things that we should repair, replace, whatever it might be. We've started it back up. The next thing we want to do is we want to analyze how efficient that boiler is. So we would encourage the use of, either you have one yourself or have a technician bring in a combustion analyzer. And at minimum, we want to be looking at it being able to tell us the O2 level, if it's generating, if that burner is generating any CO or carbon monoxide, what's the efficiency, the exhaust gas temperature, and the supplied combustion air temperature. In other words, the ambient temperature in the room. Those are the basics that we want to look at. Now, once we have that combustion analyzer in place, we start analyzing the O2 and the CO2. That's going to give us a good indication on how good our combustion efficiency is and how efficient we are. So if we find that we're in the 70 to 75% range, do we go out and buy a new burner right away? No. The first thing you want to do is you want to tune it up. And if after tune-up you're still high excess air, still generating some CO, and you're in an overall efficiency of 70 to 75%, you might want to look at that particular point at changing out the fuel drives. Do I want to go to parallel positioning as I show here and get rid of that single point positioning? Is that going to help me? That's retrofittable. That's something I might be able to do. Barring that, it's only at that point that you start to look at a new burner and make sure that that burner is properly matched to the furnace, because they have to work together in a coordinated fashion to give me optimum combustion and fuel to steam or fuel to water efficiency. So, in the final analysis, in summary, the annual boiler inspection should be leveraged for positive gain. Use the time to inspect all the equipment and piping in the boiler room. This should be part of your SOP. The walk around that boiler before you even do anything with the unit itself, with the boiler itself. Look at what it's connected to. And then properly shut the boiler down and secure it. This too should be part of your SOP. And then take the appropriate action with compromised pressure vessel, components, or the refractories. They're all there for a purpose. And please just pay special attention to the low water cutoff. It's the most important safety device on your boiler. And then apply the correct gasketing material. And then note the condition of the fuel air regulating devices. Do we need to upgrade those? Possibly. If that boiler of yours modulates a lot, it's got an old single point positioning system, think about replacing it with a parallel positioning system. And then use the time to evaluate the boiler's controls and upgrade where it makes sense. And that's where you might want to be looking at the PLC-based platform, incorporating that burner management system with it, if it's up to date and current, and look at expanding with other options that are going to save energy, such as variable speed drive and O2 trim. And above all, be safe and, of course, keep the economics in mind. How about some questions?
All right, thank you, Steve. At this time, we're going to take any questions you might have. You can submit those through the Q&A tool that is available on the event control panel of your screen. I'd like to introduce our expert panel who is joining Steve today. This includes Kevin Jellyman and Mike Zilmer. Kevin graduated from Williamson School of Mechanical Trades with an associate degree in specialized technology, electric power generation, and graduated from Cardinal Stritch University with a degree in business administration. He's been with Cleaver-Brooks for about 27 years and directly supported our service department for 11 years, working on all of our product lines from the larger industrial water tube products down through our commercial water tube products, as well as our fire tube and accessory lines. Kevin's background has allowed him to fully support our aftermarket parts area for the remaining 16 years of his experience. And then we have Mike Zilmer, who graduated from the University of Wisconsin with a degree in mechanical engineering. He's been with Cleaver-Brooks for 6 years, working in both aftermarket parts and conversions, specializing in controls upgrades. While we're waiting for some questions to come in, I just want to remind everyone that today's presentation, along with our previously recorded events, are archived on our website at cleaverbrooks.com/webinars. And for those of you who have already indicated that you wish to receive a certificate of attendance, your certificates will be emailed to you within about 1 week. If you did not previously indicate that on your registration and do wish to receive one, just add a note onto the survey that you'll be prompted to fill out after this WebEx. And with that being said, we do have a few questions that we're going to take. The first one being, do you get better turn down and better firing control with the parallel positioning system?
Hello, this is Kevin Jellyman. First, I'd like to say before I answer that, I appreciate everybody coming to the webinar and the opportunity to talk to this group. On the parallel positioning system for the fuel-air ratio control, I see that there's a couple questions related to that and the maintenance of the burner. As Steve had said, the single point positioning system really limits your turn down on a boiler. If you have two fuels, the burner or the fuel that has the least turn down really becomes the driving force for setting up the air curve. So if it's a 4-to-1 on oil, your 10-to-1 turn down that is capable on natural gas may be limited to 4-to-1 as well. So if you eliminate the single point positioning system, you move to a fuel air ratio control system, or basically a parallel positioning system. You'll have actually different controls, one for air, one for each of the fuels, so that you could set up independent fuel air ratio controls for the multiple fuels that you have. So that if you have a 10-to-1 natural gas burner, you'll be able to utilize that at the full 10-to-1 turn down. And if you've got 4-to-1 or 6-to-1 on oil, you'd be able to utilize that at its maximum fuel air ratio as well. So I hope that answers the question related to the fuel air ratio control.
All right, thank you, Kevin. Next question is, how often should combustion analysis be done today with the newer type burners?
I can take that one. How often is really kind of relative. I would say, again, it depends upon the operation of the burner itself. If that boiler is being subject to variations, let's say, in the boiler room itself as far as temperature is concerned, and it modulates a lot, I would say that combustion should be checked every month. Okay. If you have a situation where the burner is, the boiler is in an ambient condition that doesn't change, and it doesn't modulate much, it comes at a certain firing rate and stays there most of the day, then you're talking maybe every 3-4 months, something like that, maybe every 6 months that you would go through a combustion analysis. But the main thing that you want to look at here is the stack temperature. Make sure you've got a good stack thermometer in the outlet of the vent outlet or the stack outlet of that boiler. Very important, because with a efficient boiler, if that stack temperature with an efficient unit, that stack temperature is going to be between 50 and 100 degrees of the saturated temperature of the steam. If you see it deviate from that, if it goes up 40 degrees from that particular point, you've lost a % in efficiency. So the stack temperature alone, that stack thermometer, is going to tell you right there when you should be rechecking combustion, because that boiler is either scaled up or sooted up. And that's causing the elevated temperature. And if it's sooting up, that means the burner has gone out of calibration.
All right, thank you, Steve. Next question. You mentioned making sure the safety valve is piped correctly, but never got into the detail. Can you please define what is correct for high pressure steam?
Well, the piping from the safety valve itself, the outlet, should take a 90-degree bend into a standpipe. And it should then protrude into the standpipe about 6 inches, 3 to 6 inches. The standpipe then needs to be 2 pipe diameters larger than the elbow pipe and extend above the roof line with adequate support so as not to impose any pressure on the drip pan itself. You don't want to torque that safety valve, so the vent up through the roof has got to be separately supported. And it's got to be at least 2 pipe diameters larger than the outlet of the valve.
All right. Next question. Would you recommend repairing missing chunks or large refractory cracks with plastic or refractory patch?
Well, I would recommend a refractory patch, as it can be troweled in and then coated. Plastic, though it can be very effective, requires some pounding, which, depending upon the shape of the refractory overall, may cause some additional cracks to form. So I would favor, personally, refractory patch as opposed to plastic, but plastic can be used and has been used effectively. Just watch, what you're applying it to, and if that door is compromised in any other areas, this could exacerbate the problem.
Okay, we've got a few more questions here. Let's see. Are there benefits to adding a variable speed drive to a blower motor?
This is Mike Zilmer. Variable speed drives do have a lot of benefits, mostly they cut down on both energy consumption and on the wear and tear on a blower motor. They do this by enabling the blower motor to operate at only the speed needed, not at the constant speed that the motor is designed to run at. This saves energy because the airflow from the blower motor and the impeller are proportional to the motor speed, but the actual power usage is proportional to the cube of the speed. So by reducing the combustion airflow and capacity of the boiler 20%, you actually save 50% of the power consumption. So that's another one of those fuel savings that comes in. You can add a variable speed drive and really drop your electrical consumption, especially on boilers with very large blower motors.
Okay, we've got time for 1 or 2 more questions. Here's another one. What kind of fuel savings do you see after upgrading the boiler controls?
Well, that again depends upon what control is being upgraded. If we, as I mentioned before, if we replace the single point positioning with a parallel positioning, you're looking at 1/2 to 2%, depending upon the amount of modulation and so on that burner goes through. O2 trim can add 1 to 2%. Again, but you have to be careful with these. You don't just add an O2 trim system and think it's going to give you 1 or 2% in fuel savings. If the ambient temperature in the boiler room doesn't change and you don't modulate a lot, you're wasting your money on O2 trim. If you, though, have environmental conditions that change, for instance, there's a lot of boilers out there that operate outside. That would then, you've got fluctuations in temperature, you've got fluctuations in barometric pressure, relative humidity, all these things together. And if you modulate a lot, that's where O2 trim can really, really help you. Also, if you get involved with flue gas recirculation because you're trying to reduce your overall NOx limits in the burner, no-2 trim system may in fact be mandatory, especially if the recirculation rate of the flue gas is high. So it depends upon the situation. It can certainly save you, 1 to 2%, but again, the conditions have to be right for it to be able to deliver that kind of savings.
Yeah, I would just like to add that what really comes into these advanced controls is you're increasing your repeatability of your combustion. So when you have a linkage system, you set that up for that particular day and that firing rate, and you have to leave quite a bit more allowance in there for the changing temperatures, humidities, pressures. When you add the advanced controls, that system is going to adapt to the current conditions and really keep that burner firing at its most efficient level, which saves you energy.
All right, well, at this time, we've run out of time for questions. If you asked a question through the Q&A tool and we did not respond to it, we will be posting a frequently asked questions document along with a copy of this presentation on the webinar section of our website. So we will be sure to get any questions we did not get an opportunity to answer and post the answers there. If you want to reach Kevin or Mike, their contact information is listed on the last slide of this presentation, so feel free to email them with any specific questions you might have. And with that, I would just like to thank Steve on yet another wonderful presentation, and thank you, Kevin, and thank you, Mike, for being part of our expert panel.
You're welcome. Thank you.
Thank you.